Welcome back to the course on fluorescent spectroscopy. Uh, we're going to start our discussions on fluorescence sensing. I initially tried to do this as one lecture, but it was going to be a very long lecture, so I decided to break it up into a few parts that are shorter to listen to and that have a specific focus. And today we're going to talk about what is needed for doing blood gases, which is a very common clinical measurement. When someone is getting blood gases done, which is pretty common in the hospital, you have to collect the gases in a glass syringe, so there's no mixing up with the outside glasses. You have to send it to some rather large central laboratory. This takes time. A blood sample is actually needed. It's not always advisable to get samples from newborns or elderly. And we'll discuss pH and electrolytes in the following lectures, which are also part of the blood gases. So this is what many clinicians would dream of, point of care, non-invasive testings for blood gases, electrolytes, and glucose. So many physicians would love to have an instrument like this that just measures through the skin and gives you the readings that you need. That's really not possible at this time, and even the following is not possible. Taking a blood sample, smearing it on a slide, and stick it into an instrument. We're not going to talk, we'll talk about calcium, magnesium, potassium in the following lecture, but right now we're going to focus on those three things that are important for blood gases: pH, PCO2, and bicarbonate, and some others which are really almost derivatives of the previous ones. So why is this difficult? Well, non-invasive testing is hindered by the high absorption and the high scattering of tissue. It's not a problem when you're looking through a microscope and you're looking at thin tissue slices, but if you look at the absorbance of tissue over a wide range of wavelengths, basically it's very high. 10 to the third per centimeter when you get down here, and it gets lower in what's sort of the therapeutic window around 800, 900 nanometers. You can see red light through tissues. We have an example here of a mouse that you can see the red light through the tissues. So in principle, you might think you can measure some cyanin dyes through the tissues. And that's in fact true, but in spite of years of research, imaging has not been possible. There was a desire to do optical tomography. I don't think it ever turned out to be practical, but there are some good reasons why we can use this therapeutic window, although we will focus on blood samples that are extracted. What are the types of fluorescence methods that we can use? We mentioned these before, but I wanted to describe them within the framework of doing blood gases. As you know, you can do intensity-based measurements, wavelength radiometric measurements, polarization measurements, different intensities with different polarization, time-resolved measurements, and phase modulation methods. Which of these are most suitable for blood samples? Well, I think three of them are most suitable for blood samples. The problem with a blood sample is if you're working in a cuvette, you can do accurate intensity measurements. If you're working with a sample of blood, you cannot do accurate intensity measurements because of all the absorption and scattering. But if you can get rid of scattered light, the lifetimes would be the same, even if the light was attenuated greatly. by the blood. And the phase and the modulation values, if you were doing frequency domain, they would be the same if you were using a cuvette or blood. So this is important, especially for those probes that don't show spectral shifts. And a lot of the probes we'll be looking at just show changes in intensity and not a spectral shift that will allow a wavelength ratiometric measurement. In terms of doing the blood gases, the oxygens would be simple to do optically. Many metal ligand complexes are very sensitive to oxygen. I put two here for you. One a shorter lifetime than the other. You'll notice the long lifetime one is quenched a bit more. But and these sensors are very easy to fabricate. If you just put them in a little bit of silicone, they become very sensitive to oxygen, because it turns out that silicone is highly permeable to oxygen, and oxygen is very soluble in silicone. So these are not hard to visualize in a point of care sensing application. The longer lifetime ones would probably be even too quenched at normal oxygen pressures. I've emphasized the metal ligand complexes, but there are some others that I've not used personally, so I'm not as familiar with them. But there are some oxygen probes that have very long emission wavelengths, so they could potentially be used in a blood sample. And some probes even display dual singlet and triplet emission, and it's the long-lived triplet emission that's quenched by oxygen. So this would be a wavelength ratiometric probe, and this one would have to be a lifetime probe unless you added another molecule to it that was not sensitive to oxygen. This is to show you how insensitive the time resolved measurements can be to intensity fluctuations. This experiment, I always call this the hand waving experiment, because what we did is we had a slab of silicon, and inside a silicon vial, we were measuring its phase angle, and we were waving our fingers in between the light source and the detector, or the light source of the sample. And either way, the amplitude, of course, changes quite a bit when you're waving your fingers through the light beam, but the phase angle stays very constant. So if you are measuring in the frequency domain, the lifetimes will be insensitive to intensity, which will be valuable in any point of care instrument, because in a point of care instrument, the patient might move around and you might not hold the instrument exactly the same all the time, so you will have intensity fluctuations. The same is true for time-correlated single photon counting. In this case, we measured the intensity decay, and you'll excuse me, I've forgotten what molecule this was, but we measured the intensity decay over 100-fold change in intensity. So if there's going to be an intensity effect, you would expect to see it with this change, but we get exactly the same lifetime, even with a 100-fold change in intensity. So oxygen is easy to do, and intensity fluctuations might not be a problem for some of the instruments. Oh, I always found this interesting. You can even do lifetime-based image. You could even do oxygen imaging at a cellular level. This must have been pretty hard to do, because the signals are not real bright from the metal ligand complexes. But first experiment they did was to deplete the cells from oxygen and then give them oxygen. So the total lifetime goes up and down based on the oxygen concentration. In the intensity image, you see where the probe is, but you don't know what the oxygen concentration is. In the lifetime image, you see that the oxygen concentration is about the same all the time, which is exactly what one would expect. Now we're getting to a more difficult one. Carbon dioxides are needed for blood gases. We have it in one of these, the PCO2. And it's not obvious how to measure carbon dioxide by fluorescence. I'll show you there are a couple possibilities, but it's not commonly done. So CO2 cannot easily be put on a blood gas monitor. And I'm going to mention how this is done now, because if we can do the oxygen in a different way, that might make it even easier to make the blood gas instrument. So I don't know how many of you must have had oxygen saturation done in the physician's office. They put this little thing on your finger. You don't really know what it's doing, but eventually it starts giving you some readings. And what it's really giving you are wavelength ratiometric measurements. They look at the light transmission through the finger, the electronics in the instrument locks into your heartbeat, and that's why you get the heartbeat on this anyway, whether you needed it or not. And the hemoglobin spectra changes with oxygenation. So this little device here is measuring the amount of light transmitted at two different wavelengths, and from that it can calculate the oxygen saturation, not the oxygen concentration. So this would be different from the oxygen sensor I mentioned earlier. This is an oxygen saturation reading, which is also needed in the blood gas analysis. To give you an idea how difficult it has been to do CO2, in the present blood gas instruments, as they're used now, they're still using what's called the Severing-House electrode. I have a couple different images of it here. Let's see. This one isn't too bad. You have a reference of the way the way CO2 is measured is simply by the change in pH of a bicarbonate solution. So the amount of bicarbonate that's in the sample is always linked to the amount of CO2 in the sample, which is linked to the pH of the sample. So in order to measure CO2 in a blood sample, they actually have you add the blood sample, the oxygen diffuses into the buffer, and this will give you a certain electrical potential, and that potential difference tells you what the CO2 concentration is in the sample. This was invented in 1956, and it's still in use today. So I stated here that a all fluorescence method has not yet been described for blood gases, and this is what a typical instrument looks like. The blood sample can be an arterial tap or taken as a blood sample, but there's a lot of internal components which makes it expensive to do blood gases. There are a couple of opportunities for doing carbon dioxide by fluorescence. One is shown here. I don't happen to like this one very much. It's a fret-based mechanism which uses a long lifetime metal nickel complex donor. I don't know if these experiments were done with an LED, but they can be, because the modulation frequency is very low. And what was found was the phase angle changed with the amount of CO2 that was in this very complicated matrix that had silicon, ethyl cellulose, and tetraoctyl ammonium hydroxide, something I've never really worked with, but its absorption spectrum changes with the amount of CO2. That change in the absorption spectrum changes the absorbance of the metal ligand complex. You can prove that it's a fret mechanism because the lifetime is changing, or here the phase angles are changing. If this was simply due to some absorption inner filter effect, there wouldn't be any change in the lifetime. So this one can work. But I think the following is a better option for future measurements of carbon dioxide in a more simple way. In one of the earlier lectures, I mentioned to you the formation of exciteplexes, and part of that was photoinduced electron transfer. And in many aromatic molecules, you can get photoinduced electron transfer from a nearby amino group to the aromatic group. I have two structures here, but I'll only show you the data for this one. And the way this particular sensor would work is that you have a solution of your aromatic amine, and you have some CO2 in it, and the CO2 is going to react with the amine. It's going to form some bicarbonate, and it's going to form, importantly, the protonated amino form. So that would be fluorescent, whereas the non-protonated form would be weakly fluorescent or not fluorescent. In this case, it's weakly fluorescent. And going back to the very beginning, I have the frequency responses for you here. As I remember, the longest lifetime was observed at the highest PCO2 concentration. And when the PCO2 is less, the emission is weaker and the phase angle shifted to higher frequencies. So here's a calibration curve using the MMA molecule from the previous case, and you can look at the data in two ways. You can look at the mean lifetime, which you can see changes a great deal from 20 some nanoseconds up to 45 nanoseconds. So you can do that to calibrate the PCO2, or you could use the amplitude weighted lifetimes. You might remember from the past we mentioned the fractional weighted fraction of emission lifetimes, or the amplitude weighted lifetimes. The amplitude weighted lifetimes give you the molecular fractions, so you can also get that from a multi-exponential analysis. So basically I feel, actually when I started this lecture I was going to say it's not possible to do arterial blood gases by fluorescence. I didn't remember some of the things that I knew about, like the amine quenching, but now I think such an instrument is possible because first of all you can measure the O2 saturation by oximetry. That's an easy measurement, non-invasive. And you might have noticed we did not mention bicarbonate, which is down here. And surprisingly, the bicarbonate is never measured even in a blood gas analysis. The bicarbonate is calculated from the partial pressure of the CO2 and the pH of the system. So it's a calculated value, even though it's reported as an independent value. So I would conclude at this time that in vivo line or blood sample, it's still needed to do the blood gases, but it would be entirely possible to construct an instrument, a functional instrument of this type, but it is not yet possible to do all of this through the skin. Well, that is everything for our first lecture on fluorescent sensing. I did this to try to keep the lectures a little shorter. I'm guessing I've already gone about 20 minutes. Uh, and the next lecture is going to be on blood electrolytes. See you all later. Bye.